Our last speaker is Nils Hoem, PhD, MSc. He's a licensed pharmacist and master and doctorate degrees in pharmacology from the University of Oslo. He currently serves as chief scientist at Aker BioMarine in Oslo, where he has directed and participated in preclinical and clinical research, as well as in process and product development. Hoem has also been involved in basic research into Antarctic krill biology and ecology in Western Antarctica, where krill is harvested. We welcome Nils Hoem.
So thank you, and thank you for this opportunity to talk about our Lysophosphatidylcholine products and the research and product platform Lysovita. I will have to go into somewhat teacher mode and go back to the basics to show why it makes sense to focus on Lysophosphatidylcholine rather than phosphatidylcholine itself. So you have to bear over with exactly that. So I will take you through the basics. Then I will present you for a paradox that we might not think of when it comes to lipids. Then I have a solution. And then, of course, I present you with a conclusion. So let's go really back to the basics. Let's look at the definition of lipids. This is something that most of you would take for granted and never really think carefully about. But it's very broad. So let's have a look at what the Oxford Learner's Dictionary says. Any of a group of natural substances that do not dissolve in water, including plants, oils, and steroids. That's not a very specific chemical definition, I would say. Then we go to the Collins Dictionary, and I actually get it wrong, but that's a different. But any of a large group of organic compounds that are esters of fatty acids, well, that's wrong. We should tell them. Or closely related substances, usually insoluble in water, but soluble in alcohol and other organic solvents. So there we go again. They are important structural materials in living organisms. So let's go to the British. From Encyclopaedia Britannica, they say that any of a diverse group of organic compounds, including fats, oils, and certain components of membranes, that are grouped together because they do not interact appreciably with water. Very British. So the only common denominator of lipids as a chemical class is that they do not dissolve in water. And that has profound consequences for how an aqueous body like our own handle these. So let's have a look. So I would like to show you something about lipids and water solubilities. I made a list of all carboxylic acids from formic acid and all the way into the carboxylic acids that are fatty acids that we happen to call fatty acids. And here we are. If you look at the X log P column, that tells you something about how much those molecules likes lipids, that is octanol, or water. And only the shortest ones likes water, they're water soluble. And pretty soon when you elongate those acids, they will prefer octanol. And as you see, some of them are absolutely insoluble in water. There are 1 trillion times different, more of them in the octanol than in water. And the fatty acids, usually we start to define them by an X log P of 3.0, so by caprylic acid. Now, if you look at the fatty acids that is the object of this meeting, the EPA and DHA and DPA, then they are hover around 6 to 7. So they are insoluble in water. That presents a few problems. Now, first of all, this has already been done in this, but still we have a look at what this means as a diverse group of molecules. And I'm going to focus in the continuation of this on the glycerolipids, that is the neutral glycerolipids, TGs, but first and foremost on the glycerides. Well, one thing, when going through this, I realized that the Oxford English Dictionary Word of the Year 2021 was wax. Well, almost, that is. So, what about, we need to go back to some basics on glycerolipid digestion and fatty acid uptake. And this is kind of textbook stuff, but textbooks aren't always forthcoming with reality and what we exactly know by now. So, all of you know that digestion starts with intake of, in this case, lipids. It's blended, made into smaller spheres. Then the enzyme comes in, both from the mouth, from the gut, from the stomach, and from the pancreas. And they are a bunch of separated molecules by now. They still don't like water very much, so they need to be emulsified. This is the first step of their uptake. And after emulsification, they are further acted upon, because by the emulsification you get a much larger surface area that the enzymes can act on. So then the end point of that is making this into a mixed micelle, which are tiny little tight micelles brought about by bile salts. And from then on we can liberate free fatty acids, monoacylglycerols, and cholesterol. And then by diffusion or by fusion into the membrane, it can be taken up into the enterocyte through the brush border, resynthesized, combined with ApoB, made into kilomicrons, then dropped into lymph, and from there on entering into blood and then all the tissues. So first lymph, then tissues. This is the standard story, and it's a very complex process just for the digestion and the acute uptake. Now, what about short-chain FFAs? Well, they go straight through. They don't need resynthesis. They can be taken up directly, and then they go into blood, exactly like the bile salts, and then brought to the liver. So, what about lysophosphatidylcholine? The cold phosphatidylcholine that has been left with one fatty acid only. Well, papers from the 1980s, 1990s actually demonstrate that they can also be absorbed through this direct route into blood. So instead of entering the body through lymph, they can enter our bodies through the portal circulation. So they go directly to the liver. So there are two different uptake mechanisms, and this has vast consequences for their further processing in our body. Now the paradox then is that mass transport of lipids in an aqueous organism actually has to go through water, lipid barriers, and this process is dependent on the metabolic stability and directed metabolic transformation. It's dependent on water and lipid solubility, protein binding, concentration gradients, transporters, and micellar structures, that is lipoproteins, for example. So if we have a look at what this looks like, it may be fast. In some pools, it might be very slow in other pools. The important thing, let's go back. The important thing is that the overall process will never be any faster than the slowest process in the chain. And here, this is where solubility comes in. So, what about if we put in transporters? So we can put in a transporter in the membrane, or we can put in a carrier in the aqueous phase, and they will help entering that particular stage, but if there is an insoluble step in between, the overall process will not be any faster. This has consequences for the total mass that you could drive through the system. So let's have a look at real data on the uptake of DHA, and in this case administered orally as phosphatidylcholine. What we did was to synthesize this molecule, and we put in a C14 in the carboxylic group. So it's a radio-labeled experiment, and of course then we have to do it in the rat, and you have to forgive me that I've put a human in, but believe me, it's pretty much the same. Here we have the first 24 hours. So we take the substance, it's being digested, and then we will have the uptake curve. So this is in blood and in plasma, and the dots you see is the observed concentrations, and the lines are a mathematical model describing how this goes on. Now, look at this. This is the first 22 hours. So keep that in mind. Then let's squeeze it together. So this, and then we followed it for another 2 weeks. And it looks like this. So it takes one dose, you have one little pill of, or you have one meal of salmon, and your body is handling this transport-wise for 2 weeks. And recognize the undulations. And these undulations are exactly the same in the human. It's a very complex in and out of the systemic circulation situation. Now, this is a graph that I found in a paper from Kagan and co-workers from 2012 or 2013. And these are fats from C14 up to actually alpha-linolenic acid. And they're taken up in an hour, and they're gone in 10 hours. So let's put that in perspective with EPA, or DHA in this case, but EPA would be pretty much the same in this form. It's two different worlds. And what this should tell you is that the handling of these molecules are very, very different. So the fats we eat for energy are handled completely different from EPA and DHA. So what about the brain? Well, as you know, it's a fatty organ. It consists mainly of sphingolipids, glycerophospholipids, and cholesterol. It sits in the membranes. So it's made for structure and signaling. It's rich in both, very rich in LC-PUFAs, and it has a relatively high turnover rate. So how does lipids enter the brain then, given this insolubility problem? Well, first of all, in the brain, membranes are localized. Membranes localized fatty acid transporters are very important for shuffling them around the brain. And there's a lot we don't know about how lipids flow through the brain. We have the glymphatic system. We even know that there is a lymphatic system there. But there's quite a lot that we still do not know. But we know quite a few of the mechanisms that is probably involved. Now, how does PUFAs cross the blood-brain barrier? Well, the first clue came, well, there were previous clues to it, but Michael Lagarde and his group published in 2000 a paper that suggested that what is taken up into the brain is not the fatty acid, but lysophosphatidylcholine with the fatty acid on. And that was confirmed in 2014 by David Silver and his group when they published the letter in Nature on MFSD2A. Now, there is an extensive research on MFSD2A since then. Its functions is to transport fatty acid, but it also is important for the integrity and actually the formation of the blood-brain barrier itself, and also the blood-retina barrier. And this is just where it's expressed. It's expressed in the brain, it's expressed in the liver, it's expressed in our genital organs, and it is expressed in the placenta, and then a few other organs. Skin is kind of an outlier there. And this is what it looks like. Beautiful, beautiful molecule, very well understood by now. Let me go back. It's now called the sodium-dependent lysophosphatidylcholine symporter 1. If you could say that one, you can have another beer. And this is how it works. It's a classical flip-flop. It's co-transporting, it's driven by sodium gradients, and it has a 12 transmembrane alpha helix. It's the largest hydrophobic pocket known in nature. So at the very end, I would like to show you this one. This is lysophosphatidylcholine DHA that we've injected. So if you thought that these undulations that you saw over the first hours after ingesting PC DHA had something to do with absorption, you're probably wrong, because you have exactly the same kind of undulations when you inject it. And look at this. It flows out of plasma and blood in the first half hour to the first hour after you inject it. Then it comes back in a few hours, then it goes down, it comes back again, and actually it starts to come back at 22 hours again. And you can see the whole profile in logarithmic form on the top. Now, so we propose that there is a sixth form of LCO3 molecule. Together with the other ones, we should view LPC as one of the key forms that this or fatty acids takes on. And finally, it's this transport stupid, and it's a light play on what James Carville, the strategist in Bill Clinton's campaign in 1992 said, when he said it's the economy stupid. Now, finally, Lysovita is a commercial platform, but it's also a research platform, and we are more than interested to work with others to elucidate and work out the ins and outs of exactly how lysophosphatidylcholine works when it comes to both transport, but also accumulation and uptake of lipids. Thank you.